Hi, everybody. Welcome back to Lesson 5, which is entitled Another Test for Independence, because we're going to continue playing around with independent events. So let's start off with a nice little AP Stats question here. So a simple random sample of adults living in a suburb of a large city was selected. The age and annual income of each of these adults was recorded, and the resulting data is summarized in the table below. So we have how much money they make a year, and then we have which age category they fall in. So what is the probability that a person chosen at random will be in the 31 to 45 age category? So what's the probability I find someone in this 31 to 45 age category? Well, there's 89 of them, right, out of 207. So 89 divided by 207 is, we have about 0.43. It's really 0.42995, so I'll round that up to 0.43. So about 43% of the people sampled here were in this age category of 31 to 45. What is the probability that a person chosen at random from this sample whose incomes are over 50,000 will be in the 31 to 45 age category? Let's break this down. What is the probability that a person chosen at random from this sample whose incomes are over 50,000? I'm only picking people from this column. That's a condition there. That's a condition I was given there. I was given they make $50,000 plus. That's a condition I was given. What is the probability that the person will be in the 31 to 45 age category? That's what I'm actually finding the probability of. What's the probability they're in this 31 to 45 age category, given you're only picking people from this $50,000 plus category? So what's my denominator? My denominator shrunk to 96 people. From this shrunken universe, how many of them are in that 31 to 45 category? 35 out of 96. 35 out of 96 comes out to 36 and a half. 36.5, so 0.365. So I found 43% of the people sampled are in this age category. But if I just look at the people who make over $50,000 a year, only 36.5% of them are in that age category. So based on our answers above, is annual income independent of age category? So the answer of this is clearly no. Age and income are not independent. Age and income are not independent events. Why? Because the probability of picking a 31 to 45-year-old is not the same as the probability of picking a 31 to 45-year-old given they make over $50,000. So since those two probabilities aren't equal, it's less likely to find someone in this income bracket. It's less likely to find a 31 to 45-year-old in that income bracket. They are not independent events. There's an association. Something is happening behind the scenes here. So that was an AP Stats question. So if you are interested in taking AP Stats next year, you can, but you do have to reach out and talk to me, and we can talk about what is AP Stats. And also our whole next unit is statistics, which kind of sets you up for AP Stats. So let's talk if you're interested in getting some college credits next year, other than SUNY Pre-Calc, which will get you college credits. SUNY Pre-Calc is more of like more Algebra 2 the first half of this year, exponents, logs, polynomials, factoring. AP Stats is more of probability and a lot of statistical thinking, which we do in the next unit, which we're almost there because probability is a quick one. So let's keep going. The probability that Gary and Jane have a child with blue eyes is 25%. So the probability of blue, I guess I should be using a blue pen. The probability of blue eyes is 0.25. The probability they have a child with blonde hair is 50%. Probability that they have a blonde-haired child is 50%. See how I'm like breaking down this question? I'm picking out the important stuff, getting it out of the sentence, and just saying, all right, here's what I need to know. The probability they have a child with both blue eyes and blonde hair. So this is blue eyes and blonde hair, not blonde hair and not blue hair and blonde eyes. That'd be scary if that was your child. So we have blue eyes and blonde hair. That's 0.125. Determine if the events blue eyes and blonde hair are independent. Does knowing you have blue eyes affect the probability of you having blonde hair? That's what we want to know here. So let's do that. Does knowing you have blue eyes change the probability of you having blonde hair? So I'm finding the probability of blonde given you have blue eyes. So my universe shrunk. My universe shrunk to just picking the blue-eyed people, 0.25. Of those blue-eyed people, how many of them are also blonde is the question. Well, I can't put 50% up top because I know blue already happened. When we find given probabilities, the and probability goes up top. So 0.125 out of 0.25, I'm just checking to be sure, gives me 0.50. Well, wait a minute. The probability of picking blonde is 50%. The probability of picking blonde knowing you had blue eyes, did that change the probability? No, it's still 50%. So these events are independent. Blue eyes and blonde hair are independent events. Are independent. Why? The probability of blonde is the same as the probability of blonde given you had blue eyes. Knowing you had blue eyes did not change that probability. It's still 50%. That's a lot of work. Let's make it easier. So we're going to come up with another test for independence. So assume that A and B are independent events. So A and B are independent. So what does that tell me? That tells me the probability of A given B is the same as the probability of A. I was given independent events there. So A given B is the same as the probability of A. It's kind of like a flowchart proof I'm doing here. Well, wait a minute. What is A given B? Well, that's the and over B. So I'm going to make that substitution. Since they're independent, these are the same. So that tells me P of A, because they're independent, I can make that substitution equals the and over the given. But I don't have the given anymore because I know they're independent. I'm only allowed to do this if they are independent. And then if I cross multiply here, we get a nice little formula. A times B should equal the and. Probability of A times the probability of B gives me the and probability. Only if they're independent events. And this goes both ways. So A and B have to be independent. If they're independent, you can multiply them, and that gives you the probability of both occurring. This is another way to test for independence, and it's a lot faster. So use this test to quickly determine if the two events are independent in the question in the previous problem. So watch what I'm going to do. Probability of blue and probability of blonde. Blue was 25%, blonde was 50%. So what I'm going to do is I'm going to multiply them. I'm going to do blue times blonde. 0.25 times 0.50. I pick up my calculator here. If I just multiply those two events there, I get 0.125. Well, wait a second. What's the probability of blue and blonde? Blue and blonde is 0.125. So notice they're the same. If you multiply two probabilities together and get the and probability, your events are independent. So if you multiply them and get the and, they're independent. This only works if you're doing word problems. This only works if you're doing word problems. If you're given a two-way table like this, do not multiply them. Use this A given B. Use what we did in the last lesson. If I give you words and don't really give you a two-way table to work with, use this way. Multiply the two probabilities, see if it gives you the middleman. See if it gives you the middleman. So let's try this. On his way to work, Frank passes through two intersections with traffic signals. Sometimes they're green when he arrives, sometimes they're red and he must stop. Let's pray that, Frank stops at red lights. The probability he stops at the first is 0.4. The probability he stops at the second is 0.5. The probability he stops at both, so first and second, is 30%. Are these events independent? So there's two ways to go about this. You could do A given B, and just like we did before, or watch what I'm going to do. First times second. I'm going to multiply those two events together. 0.4 times 0.5 gives me 0.20. Wait a minute. Does that equal the AND probability? What's the AND probability? 0.30. I got 0.20. So are they independent? No, not independent. These events are not independent. Why? Their product did not equal the AND probability. The product of the probability of first times the probability of second did not equal the probability of first and second. So it gives us another test for independence. You can find the product. We can use the product to see if it equals the AND probability. Let's try this again. An online bookstore sells both print and digital ebooks. Customers can pay with gift card or credit card. So the probability that a print book is purchased is 60%. Print is 0.60. And the probability that they pay with a gift card is 0.2. So gift card, GG, gift card is 0.2. If these events are independent, what is the probability that a randomly selected book to purchase is print and gift card? So I'm telling you, we know they're independent. What's the AND probability? What's the AND probability? You find the product. 0.60 times 0.20 equals 0.12. That would be your AND probability. The probability of print and gift card equals 0.12. Because they're independent, I can multiply those two probabilities together. Suppose that the probability of the event ebook is purchased is 0.4. The probability the customer pays a gift card is 0.2. So they're changing it up on here. So the probability in ebook, ebook is 0.4. The probability of ebook is 0.4. And the probability of gift card is 0.2. And so let's forget about that. The probability that ebook is purchased and gift card is 0.1. So that's an AND probability. Ebook and gift card. That's 0.1. Are these events independent? Well, let's find their product. Let's do ebook times gift card. 0.4 times 0.2 comes out to be 0.08. Does that equal the AND probability? No, they're not equal. So are these events independent? These events are not independent. Why? Their product did not give me the AND. So it's going back to this idea of P of A has to equal P of A given B. It just uses that conditional probability formula to give us a new little test. It gives us that conditional. It all comes back to P of A equaling P of A given B. It's just rearranged a little bit. So it's still the same idea. It's just in a quicker, faster way to do it. I'm going to leave this last page for you to try on your own if you'd like. I think we did enough, but I do want to review with you. There's two ways to test for independence. If I give you a two-way table, find the probability of an event, and then find that same probability given the second event occurred. So you're still finding the probability of A each time. The second time, you're just adding in a condition. If I give you words, if I give you a word problem, it's a much faster to find the product. Multiply A times B. Does it equal the probability of A and B? That's the other way. So you want these always to be equal. A given B, or the product of them should equal the middle. That's how we can test for independence.